Hi, my name is Katharina and I present joint work with Claudia Diaz on our project VerLoc, Verifiable Localization in Decentralized Systems. And I will begin the whole presentation with a very simple story to give you a motivation of what this is about. In our story we have two people. We have Alice and we have a good friend Eve. And Alice has this super special copy of the book 1984 and she wants to send it to Eve. And Eve says, okay, great, but please don't send it directly to me, send it over to Socks Guy and then he'll hand it over. And the reason why they go through this extra trouble is they're on the transmission path, there is Evil Town. And Evil Town doesn't really like books like 1984 and they would just confiscate it. So if they hand it over to Socks Guy, they have this friendly proxy who takes care of secure transmission. The problem is the attacker impersonated Socks Guy. So the attacker acted like it would be outside of Evil Town and would be a nice and friendly proxy. And when Alice then sends the book, the attacker can just grab the book, confiscate it, and it's gone. So we don't have a happy ending in our story. Monster Guy wins again and we are in trouble. And this is a rather simple and stupid story, but it actually is related to a real world problem. So let's look at the same story again, but now from a more technical perspective. We have this network. We have a lot of nodes. They are connected. Not everyone with everyone, but you can reach more or less every node with a direct connection or by making one or two hops. And we have Alice and Eve again. And they are in trusted areas of the network. And we have this bad area of the network, Evil Town, that we don't trust. So when we make a transmission, when Alice wants to reach Eve, there are different options to pick a hop for the transmission. You surely would avoid any hop through Evil Town, but there are a lot of different combinations that you could use that are trusted. So in this case, we have our proxy, Socks Guy again, and we would have a safe transmission. The problem is, what about nodes that are not really where they claim to be? So what about nodes that claim to be in a trusted area of the network, but actually are in the untrusted one? That's a problem. So we have servers that lie about their locations, and we have a network that we can't really trust. And that is an actual problem in real world systems. And we want to solve that. So we have a strict to-do list, what we want to accomplish. So in the context of this problem statement, we first want to localize nodes, so get their geographical location, preferably with little to no overhead for sure. Second, we want to verify the results. So we want to compare our estimate to what they claimed. So they claimed locations. We want to see if something is wrong with that. And we have to prepare for trouble here. We have adversaries that will mess with our system. And third, to make things a bit more complicated, everything should work in a decentralized setup. So let's begin with the localization. That's a rather simple principle. So we have two nodes, A and B, and what we can do, we measure the round trip time between the nodes. So you send a ping from A to B and you wait for the response to come back. Then it takes 10 milliseconds, that's the round trip time. And we have to assume a certain speed for that transmission. And as nothing travels faster than the speed of light on our internet, this is a nice upper bound that we can use. It's a terrible overestimate, but this will do for now. So if you have a simple equation like speed times time equals distance, you can just put in all the parameters from our measurement. You have 10 milliseconds of time, the speed of light. This results in roughly 3,000 kilometers. And then we can draw the circle around A. And everything inside that circle is the area where B could actually be located. And this is what we can use for localization. So we have A and B. We measure the round trip time. We get the distance. We draw the circle. But we don't just do this once. We do it multiple times. We add another node and another node. And you already see these measurements create a lot of circles. They all agree in their intersection. So this intersection is the area where B must be located because all the measurements agree there. Now, if you look at our measurements, it's not optimal yet. So we have a rather big area. We have B and E in that area. So what we can do to improve is we just add more nodes. So when we add node Q in our measurement, get a new intersecting area, and this is where B is supposed to be located. So this is the approach that we can use to estimate a target area. It's not exact localization, but we don't need that. We just want to know the country. We want to be sure that our node is not in evil town, but in a trusted area of the network. So step 1, check. We can localize nodes, and we have little to no overhead because we just use ping measurements. It's an existing protocol. It doesn't have a lot of overhead. You don't need a lot of data. Second step, verify the results. So we have our estimates. Now what happens if the attacker just messes with us? And we look at the same setup of nodes again. But now we have a location of B. That's the real location, and we have a claimed location, the red one. So B claims to be in the red location, but the physical location is the dashed one. So now if we do measurements, we always measure the physical location. Obviously, we can't just send a ping to a virtual location, which means the timings we get and the intersections we get are for the physical location. And now if you look at this picture, you see that this is nice for the actual location, but it has nothing to do with the claimed one. So this is a problem, right? If you would just look at this, you would say, okay, something is wrong. Might be an attacker, might be very bad quality of measurements, but something is wrong. So the adversary is smart and says, okay, I claim to be here, and now I mess with the measurements because I really want to make this happen. And there are two things that can happen. First thing is you slow down a measurement. This is easy. You can always do that. You receive a ping measurement, you just hold it back, and then you send it back later. And all of a sudden 10 milliseconds became 20, and 20 is a far bigger distance than 10, which means you can act like you would be further away than you actually are. So this is easy. This is for something between A and B, where the claimed location is further away. The problem is speeding up things. So you can't just respond in advance. We take care of that. You can't just speed up the measurement because the speed of light is the maximum. We already assume that. So speeding up is a problem. And this is something that allows us to detect errors. This allows us to see if there are discrepancies in the measurements, if something is wrong with the claimed location. And then, even if it's just very lousy measurements, we have a low confidence in our decision, and it's a good thing to double check that. So, second to do, we can verify the node locations, and we can find out if something went wrong, either measurements or manipulations. In any case, we know we have a low confidence in a decision, and it's something that we shouldn't just trust. Third to do is decentralization. So all of this should work in a setting where the network is fully decentralized. And I'll spare you the details. One simple solution would be to use a broadcast channel, which means just upload all the information, all the measurements, and then each node can fetch the measurements and do their own computations, which means every node can get their own truth. And then if the majority of the network is honest, you get an honest overall result for the evaluation. Now, next thing is this question or this criticism. So this is never going to work because real networks are really noisy, which means timing measurements are very inaccurate and you can't really localize, and then your estimates are wrong, and then you can't really see if something is just noisy or attacker or whatever happened. So we build a prototype. We build this whole system in a real network with real nodes and real transmissions. So we used the NIM network. We had thousands of nodes. We sent timing measurements. We gathered all the data. We did our evaluation. Turns out, localization error in our prototype on the real internet is 60 kilometers. And 60 kilometers doesn't sound nice if you think about navigation, for example. You shouldn't be 60 kilometers off. But in our case, it's just fine, because we're just interested in countries, for example. If a node is in the country it claims to be, so if it's in the country that we trust, or in another country that we don't want to send our data through. And then 60 kilometers is nice, even in, for example, Europe, where you have a lot of countries that are rather small, and an error could be a problem. But this is still nice for finding out what the target area is and if it's trusted or not. And this brings me to the conclusion of the talk. We have a couple of lessons learned from this system and the problem statement and the implementation. First of all, we work on a system that's fully decentralized and where the locations of nodes really matter, where it makes a difference if you're in country A or in country B. We know that nodes can lie, so you can just claim a false location. You can just claim to be in a country that you're not in. So what we want to do is verify these claims and find out if someone messed with the location or the measurements, or if something just went horribly wrong with the measurements. Both are things that we want to find out. So there are three major goals that we have to achieve. First one, we have to localize the nodes, and for that we use round-trip time measurements that has very little overhead, and we can estimate where a node is. Second, we want to verify the locations. So we want to have robust estimation and want to compare it. And third, everything works in a decentralized setting. And to show that this actually works, we built a prototype in the NIM network. We verified the actual locations, and we had a location error of 60 kilometers, which is perfectly fine, even when you have a very crowded continent with a lot of smaller countries. And with this, I end my talk, and I'm thankful for your attention.